Hello, I'm Neeraj. Today I will try to discuss one important paper related to online deep clustering. For this, I will use the Facebook AI research paper and India paper. Title is Unsupervised Learning of Visual Features by Contrasting Cluster Assignments. I will try to discuss and explain this paper in a very simple way, or so that anyone can easily understand. In earlier tutorial, I have discussed about deep clustering algorithm, like how we can develop a self-supervised deep clustering algorithm. But the problem with such kind of approaches are like it keeps the entire data into the memory because it applies traditional k-means algorithms. Now suppose you have a huge amount of data, then to achieve some resource constraints, or if you have some resource constraints related issues, then online deep clustering will be a better alternative. So how they achieve this technique? For that, they have used the contrastive instance learning and changed the way when it traditional loss functions to just apply for contrastive instance learning through swept assignment based loss function or swept assignment prediction functions. So these are the changes proposed by the author. Some other changes are also proposed by the author. So I will go everything one by one. So suppose let us start. Author started with a set of images. Suppose it is coming from ImageNet or MLIST data. After that, authors have applied the augmentations. For that, authors have used multi-crop augmentations. So multi-crop augmentations means authors have used V plus 2. The authors have generated V plus 2 views for each of the images. So 2 views are global and rest of the V views are crop views. So what is crop views? Global views are very generic kind of views like flip, horizontal flip augmentations, Gaussian blur estimations, or anything may be possible. But what is the crop view? So in a crop view, authors generally select some portion of the image, zoom it, and apply something like random horizontal flip, Gaussian blur, and here authors have discussed those things. So it is like color distortions, Gaussian blur, and random horizontal flips kind of things. They have applied to each of the crop views. So that's total V plus 2 views are generated. Now, after getting all those augmented views for the images, we reset here. Suppose we take the xn, image xn. So after the augmentation t, we will get the image xnt. So till here we reached. Now the next part is authors have applied some non-linearity. So to achieve the non-linearity, they have passed it through some neural network architecture and represented this architecture through a function theta. So when we pass this, then it will be written like f theta x and t. Now we are here. After that, this is also similar. Only thing is like multi-crop view. Here it is a general type of augmentations. So after this, authors have go through the L2 norm. So why we are using L2 norm? I have already discussed this in a separate video lecture. So when we represent the data through L2 norm, we are generally able to represent the data through the surface of unit sphere. Unit sphere is the sphere whose which is actually set of points whose L2 distance means Euclidean distance from the center will be equal to 1. So when we represent all those augmented values or points at those surface, then it will help us in achieving the scale invariance property. Scale invariance means maybe the data which are coming from different sources may have a different contrast, so they will have, after augmentations and after those steps, they may have a huge differences, numerical differences in their actual values. So once we map it a unit sphere by applying L2 norm, such kind of due to scale invariance property of L2 norm, we will be able to map it on the surface of a sphere, and we can easily differentiate and identify the similarity between them. For that, we take this and apply L2 norm with this formula, and it is just divided to normalize, and after that we get Z and T. So this is the normalized L2 norm form, normalized format. Now the next part is to get the cluster code. Here authors have used, according to this paper, authors have used the spherical clusters. So spherical clusters, it generally contains K prototypes. So according to this paper, authors have used K prototypes. For example, C1, C2, like CK. And the major things that works with the spherical K-means clustering algorithm is, here we use cosine similarity to identify the similarity between the cluster centers and points. This is different from the traditional K-means algorithm. So with the help of ZT, we try to identify the cluster codes by comparing with the those prototype vectors. So suppose when we pass this to this cluster prototype centers, we will get some code. Suppose represent is at Q and T. So for Z and T, it is Q and T, Z1, Q1, Z2, Q2, like that. So we can easily get the codes. Now, the next important part is cluster assignments between views, swapped assignment between views. So this is the main part. So how authors have achieved this? For that, they have used the feature Z1 to predict the code Q2 and feature Z2 to predict the code Q1. For that, the authors have developed a different kind of loss function. So let us go through this. So now we will discuss about how the swapped assignment, loss function for swapped assignment is actually defined by the authors. So for that, to identify or to calculate the loss between two features, two augmented features, ZT and ZS, we represent it like a ZT and ZS. They have calculated the loss of predicting QS by ZT plus loss of predicting QT by ZS. So this kind of swapped loss predictions authors have used, and they take the summation of both to actually identify the loss of contrastive loss of two views ZT and ZS. Here ZT, suppose we take this part and just try to explain like how loss of ZT and QS is actually computed. So it is computed like a simple entropy kind of function where PT is defined like that. Here K is all the cluster prototypes is exponential of 1 by tau zt transpose of zt dot ck. So ck is a cluster prototype vector, and tau is actually temperature. So the concept of temperature, which is used in contrastive learning, generally used to control the learning. So actually temperature controls the learning in the presence of dissimilarity. For example, if temperature is high, then it will be less sensitive towards the dissimilarity. It will make the system less sensitive towards the dissimilarity. And if temperature is low, it will make the system highly sensitive towards those dissimilarity. So in that case, system will learn from those dissimilarities. So this way, the temperature actually controls the learning of dissimilarity between different views. So this is the part. Now, after that, authors have taken loss over all images and all pair of data augmentations for the swapped predictions problem. So for swapped predictions problem, the authors have minimized this function with respect to prototype C and parameter theta of the image encoder f theta, which are used to produce the feature ZNT. Like here, it is produced like ZNT. So for that, you can easily understand how this derivation is actually working. So take this. If you take the log of this part, then you can find that this minus this numerator minus denominator, you can see here, and QS is defined as this part, which actually represents the 1 by tau ZNT means, and then prototype vector C, and then code QNS. For NT ZNT, we are taking the code QNS swapped code, and for ZNS we are taking the swapped code QNT. And for all the images and for all the view pairs, after normalizing, we get this expansion for the swapped predictions problem, and we are actually minimizing this equations function with respect to prototype C and parameter theta of the image encoder f theta, which are used to produce the feature. Now, the next part that author explains like how we can use these functions and compute the codes online. So how to compute the codes online? For online code computations, the authors have said that how the swapped assignment functions can be represented, and we can use the entropy functions parameter with this for smoothing and mapping to get the appropriate code. So this is the actual paper, and according to the results, you can find that it is better than SimCLR results. It is little inferior compared to the supervised algorithm, but better than SimCLR based algorithm.